Okay, well, happy Monday to you. I sent back the exams, at least for everybody who completed them. Most of you did very well on it. There were a couple that people missed. There was that one recoding one with the weight that I think people didn't handle the missing cases correctly, and that's why you got that wrong. And then there was about half of you or so missed one of those Z-score questions. And if you have any questions about that, I'm glad to go through that with you and show you what you did wrong. But for the most of it, it went pretty well. Another commonly missed item was the one that asked about one of the variables in the ad health data set. It asked about the level of measurement, and it was an interval scale. People were putting ordinal. About half of you got that one wrong, but half of you got it right. So if there are questions about any of that stuff, please let me know. We won't really be going back to the Z-score stuff again or having you use that table again. However, recodes and knowing how to read descriptive statistics, which by and large most of you did very well on, yeah, you'll definitely need to continue to learn how to or know how to do that. So that's that. Okay. Well, okay, so on the agenda then here today, we're going to talk about something new. We're going to talk about ANOVA, analysis of variance. And what an analysis of variance is, it's really kind of building on the t-test. Okay, so the t-test is designed to test for group differences in some average when there's just two groups. When you have ANOVA, you can have multiple groups. You can have really just infinite number of groups if you have a huge sample size. But the groups themselves need to be at least usually about 50 people in them to be to have much statistical power into being able to not show false or type 2 errors. Just so you have statistical power to show that there's significant differences between groups. You want to have about 50 people representing each one of these groupings. But what the ANOVA is doing, before we get into the details of it, which we're going to get into a little bit, not too terribly much, but what ANOVA is doing is it's testing for differences in averages when there are more than two groups. Okay, so I have a couple questions on there asking about parental drinking and marital status. I think there are 5 marital statuses on there, or at least 4. So anyway, yeah, you wouldn't do a repeated t-test because the chances of you finding a significant result where it's really not type 1 error keeps multiplying when you do that, when you're just switching out the variable that you're testing it against. So to avoid that problem, what we do when we have multiple groups is we want to test them using an ANOVA, an analysis of variance. Okay, and so what we'll do now, let me attempt to share my screen with you and look at this PowerPoint that's up here on Moodle. There is that, and there is also a PDF on Moodle that you should please read that deals with ANOVA. It's really short, but it does. Now on this slideshow, I don't have the mathematics of how you do an ANOVA. It's more complicated than what we've done before, but it's there in that PDF. In fact, maybe I'll show it to you, and you can see what's going on. The mathematics of how one actually calculates this stuff. But we'll talk about this at a theoretical level here first before we look at how actually one would crank through the arithmetic of it. So an ANOVA stands for an analysis of variance. And so what we're doing here is imagine you can have differences between groups in some outcome. Let's take a look at, for example, race and ethnicity and alcohol consumption. So typically whites drink more than blacks, who in turn drink more than Asians. You find that a lot in a lot of large samples. But it's not as every white person drinks as much as the next white person, and every black person drinks as much as the next Black person, et cetera, et cetera. You're also going to have variation within groups. So there's going to be variation among the drinking levels within groups of whites, within Blacks, within Asians, et cetera. So when you want to know, okay, when one group compared to another group compared to another group, when you're doing simultaneous variations or simultaneous comparisons of groups and how much they drink, you want to be able to factor in the within group component. So the fact that not everybody who's white, Black, or Asian has the same level of drinking. There's variation within the group, in addition to the fact that there is going to be maybe or maybe not differences in the averages of drinking among whites, Blacks, and Asians. And so that would be the between group variance. And so what this Venn diagram thing is showing, Venn diagrams are a classic visual way of illustrating how much of one thing contributes to the whole of something that we're trying to take account of. And here it's the variation in drinking in my example. And so as it's showing here, if this line in the middle that's dividing this thing right down the middle, because the assumption is, the null hypothesis is that you're going to have an equal amount of between and within group variation here. So what's showing here graphically at least is that when you move this line to the right, more the between group variation dominates and the within group variation shrinks, which would basically mean in real terms that white people are more alike one another in terms of drinking, for example, then they are different from, or I would say, sorry, that Blacks would be more like one another and more different from whites than vice versa. So you'd have a big between group difference there if it's the case that average differences between groups in drinking really dominated, even though there's still some within group variation. Okay, so that's one way to visualize it with this Venn diagrams. Here's another way of looking at it. If you have so 3 separate distributions of drinking behavior, we'll just stick with that. And we have 3 separate bell curves in the top illustration. So this is showing that we can say again that just for the purposes of example, that the highest level of drinking, the one on the far right, is whites, in the middle Black, and then on the left Asian. Well, what this is showing is that the averages, well, the averages are different. The variation within these groups is the same. That is, they all have different averages. There may be significant different averages between the drinking or the between group drinking here. But the variation, because the bell-shaped curve is the same for all 3, then they all vary around their own means in the same way. Whereas in the bottom illustration, you could have 2 groups that basically have the same bell curve distribution, where the other one is much flatter, it's much more spread out. And so you can see how there's a lot of overlap. There's much more overlap in the second illustration down with certainly the second one, and then even the last one on the far left, the distribution on the far left. So it's showing that there's a lot of overlap in the group with the highest average drinking level with the group with the second average highest drinking level. So there's a lot of people who are from the white group and from the Black group who actually have similar levels of drinking. So much so that you might find that that there are no real average differences between groups of Blacks and whites. The average differences really only exist between whites and Asians and between Blacks and Asians. Now, this is all hypothetical. I'm just doing it based on what we generally know about drinking patterns in the United States. But this goes to illustrate this idea that even if you have 3 different averages, that there may be so much variation within that group on some behavior like drinking that it overlaps with some other group, that those two groups turn out to have actually statistically similar averages, or statistically no different averages from one another. Okay, and so that's what we're doing in ANOVA. To get back to why we're talking about this in ANOVA is accounting for the fact that you're going to have variation in drinking scores within groups, as well as an overall difference in average scores between groups. And so it has to factor that in. And that's the F ratio, or the F test, is that it's looking at the between group sample variation over the within group sample variation. And so that will give you the F score, and F ranges from 0 to positive infinity, so you can't have a negative F. If F is 1, then the variance within is equal to the variance between groups. So it's, you know, it's like a division, like 5 divided by 5 is 1. Okay, so it's going to be if the numerator is equal to the denominator, it'll be about 1. If F is less than 1, then variance within is greater than variance between groups. That means that you're not going to find significant differences between groups in some outcome like drinking behavior if F is less than 1. If F is greater than 1, and depending on how much within group variation there is, the variation between is greater than the variation within groups. And I said depending because if there is a lot more variation between groups than there is within groups, then you're going to have a statistically significant F test, meaning that there are real significant differences between racial groups and how much they drink, over and above the fact that we know that not everybody who belongs to a particular group drinks the same amount, that we're taking into account the fact that people vary individually, but there are clear identifiable differences in amounts of average drinking between these racial and ethnic groups. Okay, so that's one application of ANOVA, why you want to use that. And again, the number of groups you have can be a lot bigger than the 3-group example that I just illustrated. You could have 10, 20, 100 groups. You just need to have a big sample, and like about 50 people, 50 observations per group. If it's not people, then it could be, I don't know, companies or something like that. But you want to have a good number of them, with 50 of them in each group. Testing for mean differences between 3 or more groups is why we would do that over repeated t-tests, because repeated t-tests increase the chance of a type 1 error. Variables should be 3 or more independent from 3 or more independent samples. And now we don't have actually separate samples, but the idea again is that the scores on some outcome X for group A were not somehow directly influenced by group B, or vice versa, or by group C. And so we did this example before, but with independent samples t-tests between boys and girls. We assumed that the boys' scores were not influenced by the girls' scores, or vice versa. So there's that. So the dependent variable needs to be something then, typically that you're asking for an average that would make sense to ask for an average in. So if you're looking at like marital status and race or ethnicity, as you're looking at the relationship between those two variables, that's a chi-square. You would not be using ANOVA. ANOVA would be if you have like marital status as your grouping variable, as the independent variable that is thought to have an influence on the outcome, and then the outcome would be something like alcohol use in the past 12 months, where it would make sense to ask for an average score for that. And so your independent variables are groups, and they can be broadly construed, but I just gave you a few examples here: race, ethnicity, educational level, that kind of thing. You can group people on that. You can group people on anything that is reasonable within the social sciences. But the groups should be comprised of at least 50 people or observations in them. And then the dependent variable is something that should be measured at least the ordinal level, where, you know, it could be a Likert item, it could be something that asks an amount of how often have you done something, anything it makes sense to request an average for. That's the kind of dependent variables that you use for ANOVA. It's very, very similar to t-test. We're just broadening it out. So we are doing it with more than, with 3 or more groups. Okay. And okay, so that's the slideshow. Let me show you an example in SPSS of doing an ANOVA. All right, and so let me go back to my screen here. And here are some of the exercises I'd like to go through in class here. This is using the variables marital status and how often drink. And so that's PA61 and PA10. So these are asked of the parents in that Ad Health survey. So it's asking the parents their marital status and asking the parents how often do they drink. And I'm asking you to answer the following questions. And so which marital status has the highest average drinking, which has the lowest average drinking? Are there statistically significant differences between marital statuses and average levels of drinking, and how can you tell? And which marital statuses have statistically significant average differences in drinking? All right, so these are all questions that we can answer with the ANOVA procedure. And so the rest of the questions are pretty much the same. I'm just inserting different variables in there that would be appropriate for ANOVA analysis. All right, so marital status is going to be our independent variable then, and then drinking, how often do the parents drink, that is going to be our dependent variable. All right, so let me go to SPSS. All right. Oops. Okay. Can everybody see my SPSS screen? Is that okay? Thank you. Great. Okay. So to do this, what we want to do is we want to go down to where we see compare means. This is the same place we were at when we went to t-test. We want to go past the independent samples t-test and go down to where it says one-way ANOVA. Okay, and I'm going to, I was playing around with this, doing some other stuff earlier. Now, here is, I'll just put this back to, so we can start from the beginning. Okay, so where we want to put our independent variable in, the one that has groups is down here where it says factor. Okay, so in the t-test, it was called grouping variable, and in the one-way ANOVA, it's called factor. That's where you put the variable for which is going to indicate the independent variable, or it's the variable that it represents groups. So we're going to use this variable PA10, which is marital statuses, as this factor variable or the independent variable. So so in the marital status is hypothetically thought to have a statistical influence then on drinking, which we will put in the dependent variable list. Okay, so there is ANOVAs can be 3-way, 4-way ANOVAs where you have multiple dependent variables. We're not going to be doing that. We're doing the one-way ANOVA, and then we're going to be moving on to something called regression. And so ANOVA, the way that a lot of people use it is usually for a limited sense and just testing for differences in averages across multiple groups. And so that's what we're going to do here. So before we put that in, let's look again at our variables that we're going to plug in before we do this, just so we can see what we're dealing with, the way that they're measured anyway. So PA10 is the marital statuses variable. Okay, marital status, and yes, here is how it was measured. 1 is single, never married, 2 married, 3 widowed, 4 divorced, 5 separated. Okay, so we have 5 groups. There are going to be 5 groups that are going to be compared in terms of their average levels of drinking. And it's assumed from the ANOVA test, if there are differences, average differences in drinking between these groups, then it was an influence of the marital status on that drinking that caused those differences in average drinking between these groups. That's, at least at a theoretical level, that's what we are said to be able to conclude with a significant ANOVA test. All right, so that's the way that marital status is measured. And then I think the drinking question is PA 61, not wrong. We'll just look at that real quick. Okay, so this is in the section PA, so it was asked of the parents, and usually it was mom, biological mom answering this, not always, but oftentimes it was, how often do you drink? And it's a scale just like this, 6-point scale, never to 6 nearly every day. Okay, so we're going to look at average differences in response to this item for those 5 different groups and see if, depending on marital status, people are reporting different levels of alcohol consumption. Okay. Oops, let me go back to that. Yeah, it's compare means, one-way ANOVA. All right, so PA10 is already in there, and recall that's the independent variable. That's where we put our marital status variable. And then we want PA61 for the dependent variable, which is the drinking variable. Oh, wait, is this not? Let me do this alphabetically. Okay. We put that over there. All right. So in order to answer questions about which groups have different means, we want to go over here. We can skip over this thing that says contrasts and go to where it says post hoc. That just means after the fact. And what we want to do is we want to, I was playing around with this here. We want to click on right here where it says equal variance is assumed, LSD test. So that is a test for average differences when equal variances are assumed in the population. I'm going to click this off too. We're just going to leave it at this as the option. For this particular post hoc test, which is testing which groups specifically are different from one another. And so let's leave it right there where it says equal variance is assumed. Check the box where it says LSD, and that is a test that tests for average differences between these groups. And it is considered a statistically liberal test in the sense that it is more likely to find that there are significant differences than not compared to other comparable tests where it's a little bit more restrictive in getting into the critical region in the distribution, the F distribution, to show that it's statistically significant. So what we want to do, that LSD, it just stands for least significant difference. That's what that stands for, but that is the one that we want to click on this. And the rest of these, I know I had a couple others clicked when I first opened this, but you just want to have this one that says LSD clicked here under where it says equal variance is assumed. That's going to simplify this, but it's going to show us the test for whether or not there are differences in averages in drinking across marital status groups. Okay, so it's showing also here, it's testing this at the significance level of 0.05. And so that's the typical cutoff that most statisticians say, or in practice, that's what people say is, well, if you will call something significant, it needs to be significant at the 0.05 level or better, be considered statistically significant. Okay, so we'll hit continue. And we want to come also over here to options. And let me click out of this. All we want clicked here is where it says descriptives. We don't need to, for our purposes now, we don't need to mess around with any of this extra stuff. Just click on where it says descriptive, because that's going to provide you the descriptive statistics for drinking for each one of those marital status groups. So it's very useful to have, and you're going to need it to answer the questions. Okay. So we go ahead and hit OK. Right. Okay. So here, oops, I know you guys can't see that. Let me get back to that. Okay. So you should be able to see my SPSS output screen now. Should be one way is what I should be circling around. Can people see that? Okay. So you have this first box that it prints out. It's descriptives. And so this is giving you descriptive statistics for marital statuses. And we have, I'm not going to read all these off, but here is the number of people who are in each one of these marital statuses. The parents anyway that responded. So we got a total of 5,612. And here are the average drinking scores for each one of these groups. And so we can see here that the divorced group, just by eyeballing this, has the highest average self-reported drinking, whereas the widowed has the lowest, and everybody else is kind of in between. So the question is, are any of these averages different from one another? Are any of them different from one another? And this is done actually by comparing that average to something called the grand average. So the average across all of these groups, if that group is pulled out and its average is compared to it, does it differ significantly from that? That is what the F-test is looking at when it does its calculation, which we'll check out in a moment. But anyway, here are the averages for the drinking for each one of these groups. Here are the standard deviations. We don't need that for this exercise, but just here's what they are. The standard error is which I don't think we have talked about too much yet, but the standard error, that is related to standard deviation in it, that it is the estimate of the error found in the population. And so it is an estimate of the deviation from the average in the population, deviation from the population average, which all of this is just an estimate of. That's what inferential statistics is all about. And here is the estimated upper and lower bounds of the averages for these scores. So it's doing that. It's saying in the population, we're confident, 95% confident that the drinking levels for never married fall somewhere between 191 and 215, based on that original question that asked on a 6-point scale, how often do you drink? Okay, so it's on a 6-point scale, so you don't have anybody that's up around a 4 or a 5 or anything like that, but everybody, the average anyway, I shouldn't say everybody, the average anyway is low, but we have variation. So here, see, we have variation here as well. And so not everybody, or no one really has that exact score. There's variation around that. And we can look and see also, just examine the variation. And we can see that there is the highest variation is actually among the people who are divorced. Yeah. And so that means that divorced people are least alike in terms of how often they drink, as the standard deviation is the largest compared to all the other marital statuses. And this is just, it's showing 1 to 6 is the range of the drinking measure. Okay, so down here is where we get a look at whether or not any of these groups are different from one another with respect to drinking, self-reported drinking. And so what we see here is we're looking at what's called the sum of squares. And in that PDF, it shows how this is calculated for between groups. It's the sum of squared differences from the average for the between groups and then within groups. Comparing marital statuses and then comparing people within marital statuses is the within groups. And they each have their own degrees of freedom, which that again is based on how different the distribution could be, and still you would find the same average differences within a margin of error. But they have there's actually 2 degrees of freedom for ANOVA. There's between groups of freedom, there's between groups degrees of freedom and within groups degrees of freedom. Okay, and so there is that, and there's the mean square for both of these, which is just a transformation of this number. This divided by this will give you 13.106. So that is the overall between groups variation divided by within groups variation with some extra transformations to turn to the mean square. You have 13.106 as the F test. And so this is also a 2-tailed test over here. So we've mentioned that before, that most tests, when you're doing them, there's a 2-tailed test. You're assuming there is an effect. You don't know if it's pushing it up or down. You don't know if the effect is going to be positive or negative. It's just the conservative 2-tailed test is what we typically use. And that's showing it's statistically significant. It's significant at its p-value is 0.000. And so it's definitely significant at a higher level than 0.05. It's much smaller than 0.05. So it's statistically significant. So what this means is that there are statistically significant differences in drinking based on people's marital status. There are statistically significant differences in people's self-reported drinking based on their marital status. That's what that F test is showing us. Okay. What the F test does not tell us, though, is, well, which groups specifically are different from one another? Which groups specifically have different averages from one another? Okay, that is where you go down to this slightly more complicated looking table down here at the bottom where it says multiple comparisons. The table is daunting at first to look at, but actually it's quickly interpretable if you spend a minute taking a look at what you're doing here. Okay, so what you have over here on the far left-hand side is you have a group that's being compared to all the other groups over here on the right-hand side. And so it's comparing, in this case, single or never married to married people. The difference between the numerical or the arithmetic difference between the average of single, never married, and married people is 0.095. Okay, here's a standard error term that is used to calculate whether or not that is statistically significant. And it turns out that is not statistically significant. Okay, so between single and never married and married and how much they drink, there's actually no statistically significant difference because that is a test. That's a two-tailed test, and we need to have our two-tailed test showing at least a 0.05 or smaller. Should say at least, it needs to be 0.05 or smaller to conclude statistical significance. That 0.05 number in the p-value is just basically ubiquitous across all statistics. That's just what everybody uses. You know, it's just a 1 in 20 chance that if you redid this whole sample again, you might find something radically different. And that's the threshold for which statisticians and most all people in the data sciences agree that we shouldn't be saying something is significant if it's is a greater than 1 in 20 or 5% chance. But it's showing there's no difference there. Okay. Between the averages between single, never married, and married. Okay. So how about then between single or never married and widowed? Remember, widowed, they drink the least. All right. Now here, what we find if we do this average, then you're subtracting the average from widowed. There's the mean difference. There's the arithmetic difference between one mean subtracting from the other mean. Okay, so 0.339. So we know that's significant. So the single never married had a higher average than widowed because this is a positive number. This little star right here, though, this asterisk, tells you that it was that is a statistically significant difference. And it's also over here, you can see that the two-tailed significance test, the p-value is 0.001. Okay, and so that's smaller than 0.05. And so this is showing that there are significant differences in drinking between people who are widowed and people who are single or never married. And the single or never married are drinking significantly more than the people who are. The averages are significantly different. It's not that all people who are single or married are drinking more than all people who are widowed, right? It's not. That's not what we're saying. It's a crucial distinction here because people sometimes use statistics to say statements like that. It's the differences in the averages. They are for sure different, but the individual differences, though, that's individual differences notwithstanding. Okay, so then we look at single, never married compared to divorced. All right, and so remember, divorced were the ones that drank the most. And so when you compare single never married to divorced, the single never married are actually drinking less than the divorced. They drink. Here's the arithmetic difference. It's negative because this is a smaller average than the divorce average, and you can just confirm that by looking up here. But this is also a statistically significant difference. So the people who are divorced are self-reporting drinking more on average than the people who are single, never married. And here it is. Here's your two-tailed test. The p-value for this is 0.016, so that's smaller than 0.05. Okay, so we can conclude that is statistically significant. Okay, and so down here, we are seeing then married as being compared to all these other groups. I forgot to do separated up here. When we compare single to separated, that's not starred. Yeah, there is no significant difference there. And then the process repeats until it exhausts. There will be some redundancies here, but you will get a printout of all possible comparisons between these 5 groups in terms of their average levels of drinking. So if we go down here to married, compare married to widowed. Okay, married are drinking more on average than widowed, and the average is statistically significant, 0.243. Here is your two-tailed significance or two-tailed significance test. The p-value is 0.006, so that's a significant difference. Married compared to divorced, married people are drinking less than divorced people on average, and that is a significant difference. Then married compared to separated and married people are drinking less than the people who are separated. And so that's a statistically significant difference here. We got 0.017 is for our two-tail test. The p-value of 0.017 is smaller than 0.05. P is less than 0.05. So that is statistically different. And we can go down here and look at the rest of the comparisons, and you can see, look at widowed is significantly different than all of them. See that each one of them, you can just start eyeballing these tables, some of them, and just look for the asterisks, and you can see, okay, this widows is different from all of them. You can see that, and it's less. It's right, yeah, it's less than all of them. So widow is drinking less than all of them. And at a statistically significant level, because of course we can go back here and eyeball and we can see that widowed is the lowest, but to confirm that over and above the variation within widowed and within these other groups that it's simultaneously being compared to, that widowed is nonetheless still different from all of them, or lower than all of them. Okay, and so that is all I think I want to get to today with this first example. I can go ahead and run the other one where we're looking at, where I'm just trading out race and looking at the same thing. So let me do that. Actually, let me put this one more up there. Okay, so to run the ANOVA, one more time, it's compare means. One-way ANOVA. Okay, and we're going to take out PA10. And we're going to put in, just a moment here, I need to check to see, PA9, that's the parent's race or ethnicity. Then we're putting in for where it says factor, because that's the independent variable. PA9, somewhere. Some reason. Let me do something real quick. Start my file. Let me do this. Reason I'm. Well, did I? Is there a problem here? Just checking something here. Yeah. Well, why in the world? I'm not sure, folks, either I'm blind today or I'm just not seeing PA9 in the data list. Maybe it's past these. If you happen to see it on the screen, please scream at me, because there it is. Okay, all right. So yeah, sorry, that was PA9 is the variable that indicates the parentals the parent's race or ethnicity. So we're just going to repeat this for our last example here. And again, okay, so here's our one way. And can you all see this? Can you still see this screen? Yeah. Okay. So here again, this is the one-way ANOVA test. Here are descriptive statistics. Here are the different groups: white, black, African American, Native American, Pacific, Asian Pacific Islander. And you get the average differences for self-reported drinking, with whites drinking the most, Asians drinking the least, African Americans in the middle, as I was saying in my previous example. And so you can eyeball that and see the averages, and that can, you can answer the questions. Part of that part of those questions that can be answered just looking at this descriptive screen. Who has the highest average, who has the lowest average? You just look at the descriptive statistics. The F test here is telling you whether or not there is a if there are any statistically significant differences in the averages in drinking across these racial and ethnic groups. And it turns out with an F test of 22.092, here is your p-value at a two-tailed test. P-value is 0.000. So yes, that is a statistically significant F test, meaning that there are statistically significant differences in self-reported drinking across parent, race, and ethnicity. So, well, class is over, so I'm not gonna, you can take a look at this screen in the video if you want to watch it, but we will come back to this. I will go over this screen here, the output here of which difference, where the differences lie, but we will pick back up with this on Wednesday, and then all the other homework should be back by then, but I will most likely by Wednesday also have your next exam up to go. So I think ANOVA is the last thing we're going to be doing before the next exam. Okay, so that's that. If there's any questions, I can stick around for a little bit longer, but you are free to go, folks, and you can take a look at those other questions that I have posted on Moodle for ANOVA, but we'll just pick back up with that stuff on Wednesday. Okay. All righty. Take care, folks.